Tonight on The Sleepy Scientist, we're drifting gently through the vast cosmic ocean, where among the countless stars and swelling galaxies, we encounter some of the universe's most remarkable and misunderstood phenomena. In the quiet space of our cosmic journey, we will explore black holes not as cosmic monsters or devourers of light, but as the universe's ultimate recyclers, gentle giants that process and transform matter and energy in ways that have shaped the very fabric of existence itself. Gently, we discover that these cosmic recyclers are far from the terrifying entities often portrayed in popular imagination. Instead, they are fundamental components of cosmic evolution, processing stellar material with the patience of eons, redistributing energy across vast scales of space and time, and creating the conditions necessary for new stars, new planets, and ultimately, new possibilities for life itself. Like whispers in the night, black holes communicate with their surroundings through gravitational waves that ripple through space-time, through jets of material that stretch across millions of light years, and through the gentle glow of matter as it spirals peacefully toward these cosmic recycling centers. Tonight, we will listen to these whispers and learn their ancient stories. As our journey continues through this exploration, we will visit stellar nurseries where massive stars are born, follow their peaceful evolution through millions of years, and witness their transformation into black holes not as violent endings, but as cosmic metamorphoses that allow matter and energy to continue their eternal dance in new and wonderful forms. Let's drift into the realm of general relativity, where space and time become a unified fabric that can be gently curved and shaped by matter and energy. Here in the mathematical poetry of Einstein's equations, we find that black holes are not holes at all, but regions where space-time curves so gracefully that it creates pockets of the universe, dedicated entirely to the art of recycling cosmic materials. In the quiet space of theoretical physics, we understand that these recycling centers operate according to the most fundamental laws of nature. They conserve energy, they preserve information in ways we are still learning to appreciate, and they participate in the cosmic economy of matter and radiation with perfect efficiency. Nothing is truly lost, everything is transformed. Now we float toward our first deep understanding. Black holes are not cosmic vacuum cleaners, indiscriminately consuming everything in their path. Instead, they are selective processors, affecting only material that ventures very close to their event horizons, those gentle boundaries in space-time, beyond which the recycling process becomes inevitable and complete. Gently, we discover that most black holes spend their time in peaceful solitude, drifting through space without disturbing their cosmic neighborhoods. A black hole with the mass of our Sun, if placed where our Sun currently resides, would have an event horizon only 3 kilometers in radius. Earth would continue its orbit unchanged. The planets would maintain their peaceful dance around this new cosmic recycler, and life could theoretically continue, sustained by other sources of energy. Like whispers in the night, the mathematics of black holes reveals their true nature through the work of brilliant minds like Carl Schwarzschild, who even while serving as a soldier in World War I, found time to solve Einstein's field equations and give us our first mathematical description of these cosmic recyclers. His solutions, discovered just months after Einstein published General Relativity, showed us that black holes are natural consequences of the universe's fundamental structure. As our journey continues deeper into this cosmic recycling story, we will meet Stephen Hawking, whose gentle genius revealed that black holes are not perfectly black after all, but emit a soft radiation that allows them to slowly return their recycled energy to the universe. Over time scales so vast they make the current age of the universe seem like a brief moment. Let's drift into contemplation of the cosmic scales involved in black hole recycling. The smallest black holes we know of contain several times the mass of our Sun compressed into regions smaller than the cities we inhabit. The largest supermassive black holes, residing peacefully at the centers of galaxies, contain billions of solar masses and orchestrate the formation and evolution of their entire galactic communities. In the quiet space of deep time, these cosmic recyclers have been processing stellar material for nearly as long as the universe has existed. The first black holes may have formed when the universe was still young, perhaps from the direct collapse of primordial gas clouds. or from the first generation of massive stars that lived fast, brilliant lives before transforming into these eternal recycling centers. Now we float toward an understanding of why black holes deserve recognition as the universe's ultimate recyclers. Unlike earthly recycling, which often requires energy input and produces waste products, cosmic recycling through black holes operates with perfect thermodynamic efficiency. Matter falling into a black hole can convert up to 40% of its rest mass into pure energy, a conversion rate that makes nuclear fusion seem inefficient by comparison. Gently, we discover that this recycling process creates some of the most energetic phenomena in the universe. Quasars, those brilliant beacons visible across billions of light years, are powered by supermassive black holes recycling matter from their surroundings. Yet even these tremendous displays of cosmic recycling operate with a kind of serene patience, maintaining their output for millions of years as matter slowly spirals inward. Like whispers in the night, the accretion disks around black holes glow with the gentle heat generated by friction. As recycled matter spirals inward, these disks can extend for millions of kilometers, creating vast cosmic recycling facilities, where elements forged in stellar cores are processed and eventually either incorporated into the black hole or expelled back into space to participate in future star formation. As our journey continues through this cosmic recycling story, we begin to appreciate that black holes are not isolated entities, but integral parts of galactic ecosystems. They regulate star formation in their host galaxies, prevent runaway growth that would consume all available gas too quickly, and ensure that galactic evolution proceeds at a measured, sustainable pace across cosmic time. Let's drift into the realization that we ourselves are products of cosmic recycling. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of these elements were forged in stellar cores and recycled through space by processes intimately connected to black hole activity. Supernovae that create black holes also distribute these heavy elements throughout the galaxy, while black hole jets and outflows help transport processed material across vast distances. In the quiet space of this cosmic perspective, we see that black holes are not separate from life, but essential contributors to the cosmic conditions that make life possible. They are cosmic gardeners, pruning and shaping galactic environments to maintain the delicate balance between star formation and stellar death that characterizes healthy, life-supporting galaxies. Now we float toward a deeper appreciation of the time scales involved in cosmic recycling. While human recycling operates on time scales of days to years, black hole recycling operates across the entire history of the universe. Some of the material being processed by black holes today began its journey billions of years ago, when the first stars were forming and the universe was still young and hot. Gently, we discover that this vast temporal perspective brings a profound peace to our understanding of cosmic processes. Black holes are patient recyclers, taking millions or billions of years to process significant amounts of material. They operate according to the universe's own rhythm, neither hurried nor delayed, following the gentle laws of physics with perfect consistency. Like whispers in the night, the theoretical physics of black holes reveals layer after layer of beautiful complexity, from the event horizon to the singularity at the center, from the ergosphere of rotating black holes to the subtle quantum effects near the horizon. Every aspect of black hole physics contributes to their role as cosmic recyclers. As our journey continues into the heart of black hole science, we will explore each of these phenomena with the gentle curiosity of scientists who have spent lifetimes contemplating these cosmic recyclers. We will learn how black holes form, how they grow, how they interact with their surroundings, and ultimately, how they slowly evaporate back into the quantum vacuum from which all things emerge and to which all things eventually return. Let us drift into our exploration with minds open to wonder and hearts at peace with the vast scales of cosmic time and space. In the gentle darkness of a black hole's event horizon, we will find not terror but beauty, not destruction but transformation, not endings but new beginnings in the eternal cosmic recycling that connects all things across space and time. In the quiet space of preparation for our deep dive into black hole science, let us remember that we are embarking on a journey of discovery that has occupied some of humanity's greatest minds for over a century. From Einstein's initial resistance to the idea of black holes, to today's direct observations of these cosmic recyclers, we are following a path of gradually unfolding understanding that reveals the universe to be more beautiful and more interconnected than we ever imagined. Now we float toward the first major section of our exploration, where we will gently examine the fundamental nature of black holes themselves, what they are, how they fit into the cosmic recycling system, and why they represent some of the most elegant solutions to the equations that govern our universe. As our journey continues into the heart of cosmic recycling, we encounter our first deep truth. About black holes, they are not holes at all, but regions of space-time, where the universe has folded itself into configurations of such elegant mathematical beauty that they serve as perfect recycling centers for matter and energy. Gently, we discover that to understand black holes, we must first understand the nature of space-time itself. In the quiet space of Einstein's general relativity, space and time are not separate entities but form a unified fabric that can be curved and shaped by the presence of matter and energy, like a gentle river that flows around obstacles, creating eddies and currents. Space-time flows around massive objects, creating the gravitational effects we observe. Like whispers in the night, the mathematics of general relativity tells us that when matter becomes sufficiently concentrated in a small region of space, it creates curvature so extreme that space-time essentially closes in on itself, forming a boundary beyond which the normal rules of escape no longer apply. This boundary, the event horizon, is not a physical surface but a gentle mathematical construct that separates the cosmic recycling center from the rest of the universe. Now we float toward an understanding of what it truly means for space-time to be curved in this way. Imagine a cosmic recycling facility where the architecture itself guides materials along predetermined paths toward processing centers. The curvature of space-time around a black hole creates natural pathways that direct matter and energy inward with the same inevitability that water flows downhill. Not because of any malevolent force, but because of the gentle geometry of existence itself. In the quiet space of this geometric understanding, we realize that black holes are not active consumers but passive processors. They do not reach out to grab material from their surroundings. Instead, they create conditions where matter that ventures too close becomes part of the cosmic recycling, processed through the natural operation of physical laws. Let's drift into contemplation of the different types of cosmic recyclers that populate our universe. The most common are stellar mass black holes, formed when massive stars complete their life cycles and undergo the gentle transformation from nuclear-burning giants to compact recycling centers. These stellar mass black holes typically contain between 3 and 20 times the mass of our Sun, compressed into regions just a few kilometers in radius. Gently, we discover that the formation of stellar mass black holes is not a violent explosion but a quiet implosion, a stellar core's peaceful surrender to the overwhelming gravitational attraction of its own mass. When a massive star exhausts its nuclear fuel, the outward pressure that has supported it for millions of years can no longer balance the inward pull of gravity. The core collapses in less than a second. But this collapse is more like a gentle sigh than a violent convulsion. As our journey continues through the spectrum of cosmic recyclers, we encounter intermediate mass black holes, mysterious entities that bridge the gap between stellar mass and supermassive black holes. These recyclers contain hundreds to thousands of solar masses, and may form through the gradual accumulation of material by stellar mass black holes, or through the direct collapse of dense stellar clusters in the peaceful environment of globular clusters. Like whispers in the night, these intermediate mass black holes remain largely hidden from our direct observation, but their presence is suggested by subtle gravitational effects on nearby stars, and by the gentle X-ray emissions from material being processed in their cosmic recycling centers. They remind us that the universe operates on scales both vast and intimate, with recycling processes occurring at every level of cosmic organization. Now we float toward the giants of cosmic recycling, supermassive black holes that reside peacefully at the centers of galaxies. These cosmic recyclers contain millions to billions of times the mass of our Sun, yet they occupy regions smaller than our solar system. The supermassive black hole at the center of our own Milky Way galaxy, known as Sagittarius Asterisk, contains about 1,000,000 solar masses and sits quietly at our galactic center, recycling material at a rate so gentle that it produces only modest emissions of radiation. In the quiet space of galactic centers, these supermassive recyclers serve as cosmic anchors, providing the gravitational scaffolding around which entire galaxies organize themselves. They are not cosmic tyrants ruling their galactic domains through fear, but rather gentle conductors orchestrating the slow, beautiful symphony of galactic evolution across billions of years. Gently, we discover that the relationship between supermassive black holes and their host galaxies is one of peaceful coevolution. As galaxies form and grow through the gradual accumulation of gas and a gentle merger of smaller systems, their central black holes grow alongside them, processing material at exactly the rate needed to maintain galactic health and stability. Let us drift into an exploration of the event horizon, that gentle boundary that defines the cosmic recycling center. The event horizon is not a physical barrier, but a mathematical surface that marks the point of no return for matter and energy entering the recycling process. From the outside universe, this boundary appears as a perfectly spherical surface for non-rotating black holes, or a slightly oblate spheroid for rotating recyclers. Like whispers in the night, the physics of event horizons reveals one of the most beautiful aspects of cosmic recycling: time dilation. As matter approaches the event horizon, time itself slows down relative to distant observers. This means that the recycling process occurs with infinite patience. From the perspective of the outside universe, material falling toward a black hole appears to slow down and fade away, taking literally forever to cross the event horizon as seen from a safe distance. As our journey continues deeper into the nature of these cosmic recyclers, we must contemplate the concept of the singularity, the theoretical center of a black hole, where density becomes infinite and space-time curvature becomes extreme beyond our current understanding. Yet even this seemingly exotic concept need not disturb our peaceful contemplation, for the singularity is hidden from the outside universe by the event horizon, and many physicists believe that quantum effects will ultimately resolve the apparent infinities into something more gentle and comprehensible. Now we float toward an understanding of rotating black holes, known as black holes after the mathematician Roy Kerr, who first described their geometry. These cosmic recyclers possess angular momentum, spinning with the accumulated rotation of all the material they have processed over their lifetimes. The geometry of space-time around a rotating black hole is more complex than that around a stationary one, creating additional opportunities for cosmic recycling through processes that can extract energy from the black hole's rotation itself. In the quiet space around a rotating cosmic recycler, we find the ergosphere, a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. Material in the ergosphere is forced to rotate along with space-time, creating conditions where energy can be extracted from the black hole. Through the Penrose process, a gentle mechanism by which the universe can tap into the rotational energy stored in these cosmic recyclers. Gently, we discover that the Penrose process represents one of the most elegant examples of cosmic recycling. Matter entering the ergosphere can split into two parts, with one part falling into the black hole while the other escapes with more energy than the original particle possessed. This energy comes from the black hole's rotation, gradually slowing down the cosmic recycler while providing energy to the surrounding universe. A perfect example of the universe's commitment to energy conservation even in the most extreme environments. Like whispers in the night, the theoretical framework describing black holes reveals that these cosmic recyclers obey fundamental thermodynamic laws analogous to those governing more familiar systems. Black holes have temperature, entropy, and participate in energy exchanges with their surroundings in ways that maintain the universe's overall thermal and informational balance. As our journey continues through the fundamental physics of cosmic recycling, we encounter Hawking radiation, perhaps the most subtle and beautiful aspect of black hole physics. Stephen Hawking's gentle genius revealed that black holes are not perfectly black, but emit a soft thermal radiation due to quantum effects near the event horizon. Let's drift into the quantum mechanical understanding of this process. In the quiet space near a black hole's event horizon, the quantum vacuum constantly creates pairs of virtual particles that normally annihilate each other almost instantly. However, when this process occurs near the event horizon, one particle from each pair occasionally falls into the black hole, while its partner escapes to infinity, becoming real radiation that carries energy away from the cosmic recycler. Now we float toward appreciation of the incredible gentleness of Hawking radiation. For a black hole with the mass of our Sun, the temperature of this radiation is only about 1/10,000,000th of a degree above absolute zero, colder than the cosmic microwave background radiation that fills the universe. This means that stellar mass black holes are actually absorbing more energy from the cosmic background than they emit through Hawking radiation, causing them to grow very slowly over cosmic time. In the quiet space of this quantum understanding, we realize that Hawking radiation provides the ultimate mechanism for cosmic recycling, over time scales so vast they dwarf the current age of the universe. By factors of billions, black holes will slowly evaporate through this process, returning all their processed material to the universe in the form of elementary particles and radiation. Gently, we discover that smaller black holes evaporate faster than larger ones, following an inverse relationship where the evaporation rate is proportional to the inverse square of the black hole's mass. This means that hypothetical microscopic black holes would evaporate almost instantly, while supermassive black holes will persist for times approaching 10,100 years, numbers so large they stretch our imagination to its limits. Like whispers in the night, the mathematics of Hawking radiation connects black hole physics to the deepest principles of quantum mechanics and thermodynamics. The entropy of a black hole, a measure of the information it contains, is proportional to the area of its event horizon, rather than its volume, suggesting profound connections between gravity quantum mechanics and information theory that we are still learning to understand. As our journey continues through the theoretical landscape of cosmic recycling, we must acknowledge the profound mystery that surrounds the ultimate fate of information that falls into black holes. This information paradox, as it has come to be known, represents one of the deepest puzzles in modern physics and touches on fundamental questions about the nature of reality itself. Now we float toward contemplation of this mystery with a peaceful acceptance that not all questions have immediate answers, and that the universe's deepest secrets reveal themselves gradually to patient inquiry. The information paradox asks whether information that falls into a black hole is truly lost when the black hole eventually evaporates through Hawking radiation, or whether it is somehow preserved and returned to the universe in subtle correlations within the radiation itself. In the quiet space of theoretical physics, various solutions to this paradox have been proposed, each offering its own perspective on the nature of cosmic recycling. Some suggest that information is never truly lost, but becomes encoded on the event horizon itself, accessible in principle though not in practice to external observers. Others propose that the interior and exterior of black holes are quantum mechanically entangled, in ways that preserve information even as it appears to be lost. Gently, we discover that these theoretical explorations are not mere academic exercises, but touch on the most fundamental questions about the nature of physical law. The resolution of the information paradox may require new understanding of quantum gravity, the long-sought theory that will unify Einstein's general relativity with quantum mechanics and provide a complete description of cosmic recycling at the deepest level. Let's drift into consideration of how these cosmic recyclers reveal themselves to our observation. Since black holes themselves emit no light, we must study them through their interactions with surrounding matter and through their gravitational effects on nearby objects. This indirect approach has led to some of the most beautiful discoveries in modern astronomy. Like whispers in the night, binary systems containing black holes speak to us through the X-ray emissions produced as material from a companion star is gently processed through the cosmic recycling center, as gas from the companion star spirals inward through an accretion disk. Friction heats it to temperatures of millions of degrees, causing it to glow brilliantly in X-rays before disappearing beyond the event horizon. As our journey continues through observational black hole astronomy, we encounter the gentle gravitational influences that these cosmic recyclers exert on their surroundings. Stars orbiting near the supermassive black hole at our galactic center follow elliptical paths that allow us to measure the recycler's mass with extraordinary precision. Some of these stars approach within just a few light hours of the event horizon, experiencing gravitational fields billions of times stronger than Earth's gravity, yet following their orbits with clockwork precision according to the laws of celestial mechanics. Now we float toward appreciation of one of the most revolutionary developments in black hole astronomy, the direct detection of gravitational waves from merging black holes. These cosmic recyclers, when they spiral into each other in the final moments of binary evolution, create ripples in spacetime itself that propagate across the universe at the speed of light, carrying information about the most extreme recycling events in cosmic history. In the quiet space of gravitational wave observatories like LIGO and Virgo, these spacetime ripples are detected as incredibly tiny distortions, changes in distance, smaller than 1/10,000th the width of a proton. Yet from these whisper-soft signals, we can reconstruct the entire story of black hole mergers, the masses of the original recyclers, their spins, the distance to the merger, and the properties of the final black hole created by the combination of two cosmic recycling centers. Gently, we discover that gravitational wave astronomy has opened an entirely new window on cosmic recycling, allowing us to study black hole mergers across the entire observable universe. Each detection represents the combination of two cosmic recyclers into a single, more massive recycling center, accompanied by the conversion of several solar masses worth of matter into pure gravitational wave, energy radiated into space. Like whispers in the night, these merger events reveal that black holes are far more common than we once thought, and that the merger rate throughout cosmic history has been sufficient to gradually increase the population of more massive cosmic recyclers while redistributing matter and energy on the largest scales. As our journey continues deeper into the nature of cosmic recyclers, we prepare to explore how these remarkable entities come into existence through natural processes operating throughout the universe's history. The formation of black holes represents not violent destruction but peaceful transformation, stellar evolution reaching its natural conclusion, and matter reorganizing itself into the most efficient recycling centers known to physics. Let us drift into our next phase of exploration, with gratitude for the elegant mathematical framework that allows us to understand these cosmic recyclers, and with peaceful anticipation of the stories we will discover about stellar birth, evolution, and transformation into the universe's ultimate recycling facilities. In the quiet space of preparation for this next phase, we remember that we are contemplating processes that have been shaping the universe for nearly its entire history, creating the cosmic infrastructure necessary for the complex chemistry of life and the ongoing evolution of galaxies across cosmic time. Now we float toward the gentle origins of cosmic recyclers, beginning our story in the vast stellar nurseries where massive stars are born, from the slow gravitational collapse of gas and dust clouds. In the quiet space of these cosmic maternity wards, the seeds of future black holes begin their journey as the most massive and luminous stars in the galaxy. As our journey continues into stellar evolution, we witness the peaceful progression from stellar birth to the eventual formation of cosmic recycling centers. This process unfolds over time scales measured in millions of years. For the most massive stars, brief by cosmic standards but vast compared to human experience, allowing us to contemplate each stage with the gentle patience that cosmic processes deserve. Gently, we discover that the most massive stars, those destined to become black holes, begin their lives as gravitational instabilities within giant molecular clouds. These clouds, composed primarily of hydrogen and helium with traces of heavier elements recycled from previous generations of stars, undergo slow collapse under their own gravity. As the cloud contracts, it fragments into smaller condensations, each of which may eventually become a star. Like whispers in the night, the physics of stellar formation reveals how gravity and gas pressure reach a delicate balance that determines the final mass of each star. The most massive protostars accumulate material rapidly from their surrounding envelopes, growing to dozens of times the mass of our Sun while still in their infancy. These stellar giants will live fast, brilliant lives, burning through their nuclear fuel at prodigious rates while generating the heavy elements that will eventually be recycled throughout the galaxy. Let's drift into contemplation of the nuclear fusion processes that power massive stars throughout their lives. In the quiet space of stellar cores, temperatures reach hundreds of millions of degrees, hot enough to fuse hydrogen into helium, helium into carbon and oxygen, and ultimately to create elements as heavy as iron through successive burning phases. Each fusion reaction releases energy that travels slowly outward through the star, taking thousands of years to reach the surface and illuminate the surrounding space. In the quiet space of stellar interiors, we witness the gentle hierarchy of nuclear burning that characterizes massive star evolution. Hydrogen burning in the core sustains the star for most of its lifetime, maintaining the outward radiation pressure that balances gravitational collapse. When the hydrogen in the core is exhausted, the core contracts and heats up, initiating helium burning while hydrogen continues to burn in a shell surrounding the core. Now we float toward understanding of the successive burning phases that mark the approach toward black hole formation. After helium burning creates carbon and oxygen, the stellar core continues to contract and heat up, eventually reaching temperatures sufficient for carbon burning, then neon burning, oxygen burning, and finally silicon burning, the last nuclear process that can generate energy within stellar cores. Gently, we discover that silicon burning produces iron peak elements, iron, nickel, and cobalt, that represent the end of the energy-generating nuclear fusion chain. Unlike lighter elements, iron cannot be fused to release energy instead. Fusing iron requires energy input. When a massive star's core becomes dominated by iron, its nuclear fires are gently extinguished, and the star prepares for its final transformation. As our journey continues through the final moments of massive star evolution, we witness not a violent explosion but a quiet implosion. With nuclear burning no longer able to generate the outward pressure needed to support the star, against its own gravity, the iron core begins to collapse. This collapse accelerates rapidly as electrons and protons are crushed together to form neutrons, releasing a flood of neutrinos that carry away vast amounts of energy. Like whispers in the night, the core collapse proceeds according to the fundamental laws of physics, with gravity gently but inexorably compressing matter to densities exceeding those in atomic nuclei. If the core's mass exceeds about 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, not even the degeneracy pressure of neutrons can halt the collapse, and the core continues its gravitational contraction to form a black hole. Let's drift into appreciation of the remarkable fact that this core collapse, despite involving energies that dwarf anything we can produce on Earth, proceeds with perfect adherence to physical law. The formation of a black hole is not a breakdown of physics but its ultimate expression, matter, and energy following the logical consequences of general relativity, to create a cosmic recycling center of unprecedented efficiency. In the quiet space of this transformation, we understand that the newly formed black hole contains all the processed nuclear fuel from the star's lifetime, along with the gravitational binding energy released during collapse. This energy will power the cosmic recycler throughout its existence, enabling it to process additional material that falls within its gravitational influence. Over cosmic time, now we float toward understanding of the supernova explosion that often accompanies black hole formation, while the stellar core collapses to form a cosmic recycler. The outer layers of the star experience a very different fate. The shock wave generated by core collapse propagates outward through these layers, eventually accelerating them to thousands of kilometers per second and dispersing them into interstellar space. Gently, we discover that this supernova explosion serves as a cosmic recycling distribution system, spreading the heavy elements forged in the star's core throughout the local region of the galaxy. Carbon, oxygen, silicon, iron, and dozens of other elements essential for rocky planets and life itself are gently scattered across hundreds of light years, enriching the interstellar medium for future generations of star formation. Like whispers in the night, supernova remnants continue to glow for thousands of years after the initial explosion, their expanding shock waves heating the surrounding interstellar gas and creating some of the most beautiful structures visible to our telescopes. These remnants serve as monuments to stellar transformation and cosmic recycling, reminding us that stellar death is really stellar metamorphosis. As our journey continues through the story of black hole formation, we encounter the fascinating possibility of direct collapse black holes, formed in the early universe through processes quite different from stellar evolution. In the quiet space of the cosmic dark ages, before the first stars had formed, massive gas clouds composed almost entirely of hydrogen and helium could undergo direct gravitational collapse to form intermediate mass, or even supermassive black holes. Let's drift into contemplation of these primordial cosmic recyclers. In the early universe, before stellar nuclear synthesis had created significant quantities of heavy elements, gas clouds could grow to much larger sizes than is possible today. Without dust grains and heavy elements to radiate away heat efficiently, these primordial clouds remained hot and could accumulate masses of millions of solar masses before undergoing collapse. In the quiet space of early cosmic time, these direct collapse events may have created the seeds of the supermassive black holes we observe at the centers of galaxies today. Rather than growing slowly from stellar mass seeds through accretion over cosmic time, some supermassive cosmic recyclers may have formed directly with substantial masses, providing the gravitational anchors around which the first galaxies assembled. Now we float toward consideration of another pathway to black hole formation, the gradual accumulation of material by neutron stars until they exceed the mass limit. For neutron degeneracy support, neutron stars formed in supernovae with core masses just below the black hole threshold can later accrete material from companion stars in binary systems, slowly growing until they reach the point where gravitational collapse to a black hole becomes inevitable. Gently, we discover that this accretion-induced collapse represents one of the gentlest pathways to cosmic recycler formation. Unlike the dramatic core collapse of massive stars, the transformation of a neutron star into a black hole through accretion can occur gradually, over millions of years, with the neutron star slowly approaching and eventually crossing the mass threshold for black hole formation. Like whispers in the night, theoretical physics suggests the possibility of primordial black holes, formed through density fluctuations in the very early universe, perhaps during the inflationary epoch that occurred in the first fraction of a second after the Big Bang. These hypothetical cosmic recyclers could have a wide range of masses, from microscopic quantum black holes to objects more massive than stars, depending on the specific conditions during their formation. As our journey continues through the various formation mechanisms for cosmic recyclers, we appreciate the diverse pathways through which the universe creates these remarkable entities. Each formation mechanism operates according to the same fundamental physical principles, but produces black holes with different characteristics and evolutionary histories. Let's drift into contemplation of how black hole formation connects to the larger story of cosmic evolution. The heavy elements forged in massive stars and distributed by supernovae provide the raw materials for terrestrial planets and the complex chemistry of life. Meanwhile, the black holes formed through stellar collapse serve as cosmic recycling centers that will continue processing material for billions of years, shaping the evolution of galaxies and the distribution of matter throughout the universe. In the quiet space of this cosmic perspective, we see that black hole formation is not an ending but a beginning, the transformation of stellar material into cosmic recycling infrastructure that will serve the universe throughout its future evolution. Each newly formed black hole becomes a processing center capable of converting matter into energy with unprecedented efficiency, participating in the cosmic economy of mass and energy that governs galactic evolution. Now we float toward appreciation of the remarkable fact that black hole formation is both common and special throughout cosmic history. Common because massive stars form continuously in star-forming galaxies, ensuring a steady production of new cosmic recyclers. Special because each black hole formation event represents a unique transformation that creates a permanent new component of cosmic infrastructure. Gently, we discover that the current population of stellar mass black holes in our galaxy represents the accumulated result of billions of years of stellar evolution and transformation. Estimates suggest that the Milky Way contains millions, or perhaps tens of millions of stellar mass black holes, most of them quietly drifting through space as solitary cosmic recyclers, processing material only when they encounter gas clouds or stellar companions. Like whispers in the night, the formation processes we have explored set the stage for the cosmic recycling activities that define black hole behavior throughout their existence. Once formed, these cosmic recyclers begin their patient work of processing matter and energy according to the elegant principles of general relativity and quantum mechanics. As our journey continues toward understanding black holes as cosmic recyclers, we carry with us the peaceful knowledge that these remarkable entities arise naturally from stellar evolution and cosmic dynamics. They are not cosmic accidents or anomalies, but integral components of the universe's matter and energy processing infrastructure. Let us drift into our next phase of exploration, the detailed mechanisms through which black holes function as the universe's ultimate recyclers, with appreciation for the elegant transformation processes that create these cosmic processing centers and prepare them for their roles in galactic evolution and cosmic recycling. In the quiet space between formation and function, we pause to reflect on the beautiful continuity of cosmic processes, how stellar birth leads to stellar evolution. Stellar evolution leads to transformation, and transformation leads to new possibilities for cosmic recycling that will shape the universe's future development across vast scales of space and time. Now we float toward the heart of our cosmic recycling story, where we will witness the elegant mechanisms through which black holes process matter and energy with an efficiency that surpasses any recycling system we know. In the quiet space around these cosmic recyclers, we discover recycling facilities of breathtaking beauty and sophistication, operating according to the fundamental laws of physics, with perfect consistency across billions of years. As our journey continues into the realm of cosmic recycling, we encounter our first major recycling component, the accretion disk. Like whispers in the night, matter approaching a black hole does not fall directly inward, but instead forms a rotating disk of material that spirals slowly toward the event horizon, creating vast cosmic recycling facilities that can extend for millions of kilometers around the central recycler. Gently, we discover that accretion disks form naturally whenever matter with angular momentum approaches a black hole, just as water spiraling down a drain forms a rotating vortex. Matter falling toward a cosmic recycler conserves angular momentum by forming these beautiful disk structures. The physics governing accretion disk formation is the same, whether we consider water draining from a bathtub or gas from a disrupted star being processed by a supermassive black hole. In the quiet space of accretion disk physics, we witness one of the universe's most elegant recycling mechanisms. As matter spirals inward through the disk, friction between different layers causes the material to lose angular momentum and energy. This energy is not lost but converted into heat, causing the disk to glow with temperatures that can reach millions of degrees in the inner regions. Near the black hole, let's drift into contemplation of the remarkable efficiency of this cosmic recycling process. As matter spirals through an accretion disk toward a black hole, up to 42% of its rest mass can be converted into energy, an efficiency that makes nuclear fusion seem wasteful by comparison. This energy radiates away as electromagnetic radiation across the entire spectrum, from radio waves to gamma rays, creating some of the most luminous objects in the universe. Like whispers in the night, the structure of accretion disks reveals layer upon layer of beautiful physics. The inner regions, closest to the black hole, rotate at nearly the speed of light and glow with the blue-white heat of stellar surfaces. Moving outward, the temperature gradually decreases, creating a rainbow spectrum of thermal emission that tells the story of cosmic recycling in exquisite detail. Now we float toward understanding of the magnetic fields that thread through cosmic recycling disks, creating additional pathways for energy transport and matter processing. These magnetic fields generated by the motion of electrically conducting plasma in the disk can become twisted and amplified until they dominate the disk's dynamics, launching jets of material perpendicular to the disk plane at velocities approaching the speed of light. Gently, we discover that these relativistic jets represent one of the most spectacular manifestations of cosmic recycling. Material that enters the recycling process through the accretion disk can be redirected and accelerated outward along magnetic field lines, carrying energy and processed material across vast distances, sometimes extending for millions of light years from the central black hole. As our journey continues through the physics of cosmic recycling, we encounter the magnetorotational instability, a subtle process that enables efficient angular momentum transport within accretion disks. This instability, driven by the interaction between magnetic fields and differential rotation, ensures that material can spiral inward at just the right rate to maintain stable disk structure, while maximizing recycling efficiency. In the quiet space of magnetohydrodynamic physics, we appreciate how cosmic recycling operates through the interplay of gravity, rotation, magnetic fields, and thermal pressure. Each of these physical processes contributes to the overall efficiency of the recycling system, creating conditions where matter and energy are processed with remarkable elegance and converted into forms that can be redistributed throughout the galaxy. Like whispers in the night, the thermal structure of accretion disks reveals the gentle temperature gradients that characterize cosmic recycling facilities. The disk's temperature decreases as an inverse power of distance from the black hole, creating natural zones where different physical processes dominate and different types of recycling occur. Let's drift into contemplation of the time scales involved in accretion disk recycling. While material in the innermost regions of the disk may complete an orbit in just minutes, material in the outer disk may take thousands of years to spiral inward to the recycling center. This range of time scales creates a cosmic recycling facility that operates simultaneously on human time scales and geological time scales, processing material with patient efficiency across vast ranges of cosmic time. Now we float toward the most subtle and beautiful aspect of cosmic recycling: Hawking radiation. In the quiet space near black hole event horizons, quantum mechanical effects create a gentle mechanism through which cosmic recyclers slowly return their processed material to the universe in the form of elementary particles and thermal radiation. Gently, we discover that Hawking radiation emerges from the quantum mechanical properties of vacuum itself. The vacuum is not empty, but filled with virtual particle pairs that constantly appear and disappear according to the uncertainty principle of quantum mechanics. Near a black hole's event horizon, the intense gravitational field can separate these virtual pairs, allowing one particle to escape to infinity while its partner falls into the recycling center. As our journey continues into quantum black hole physics, we witness the remarkable process through which this particle creation gradually reduces the black hole's mass. Each escaping particle carries away a tiny amount of energy, causing the cosmic recycler to slowly evaporate over time scales that stretch our imagination to its limits. Like whispers in the night, the mathematics of Hawking radiation reveals that smaller black holes evaporate faster than larger ones, following an inverse relationship that ensures cosmic recycling operates on appropriate time scales. For different mass ranges, stellar mass black holes evaporate so slowly that they will outlive the current universe by factors of billions, while hypothetical microscopic black holes would evaporate in fractions of a second. In the quiet space of this quantum understanding, we appreciate that Hawking radiation provides the ultimate cosmic recycling mechanism, a process that ensures no information or energy is permanently locked away in black holes, but is eventually returned to the universe in processed form. This quantum evaporation process connects black hole physics to the deepest principles of thermodynamics and information theory. Let's drift into contemplation of the temperature of Hawking radiation, which is inversely proportional to the black hole's mass. For a solar mass black hole, this temperature is incredibly cold, only about 60 billionths of a degree above absolute zero. This means that stellar mass cosmic recyclers are actually colder than the cosmic microwave background radiation, causing them to absorb more energy from their surroundings than they emit through Hawking radiation. Now we float toward understanding of how cosmic recycling through Hawking radiation will eventually dominate the universe's future evolution. In the quiet space of deep cosmic time, long after the last stars have formed and died, black holes will be the primary remaining sources of energy in the universe, slowly evaporating through Hawking radiation and providing the only remaining energy source for hypothetical future civilizations. Gently, we discover that the final stages of black hole evaporation may involve dramatic increases in Hawking radiation as the cosmic recycler's mass approaches zero. The temperature of Hawking radiation increases as the black hole shrinks, potentially creating brilliant flashes of high-energy particles, and gamma rays as the ultimate conclusion of the cosmic recycling process. As our journey continues through the quantum aspects of cosmic recycling, we encounter one of the deepest mysteries in physics, the information paradox. This puzzle asks whether information that falls into a black hole is truly lost when the black hole evaporates through Hawking radiation, or whether it is somehow preserved and encoded in subtle correlations within the radiation itself. Like whispers in the night, various proposed solutions to the information paradox suggest that cosmic recycling may be even more sophisticated than we initially realized. Some theories propose that information falling into black holes becomes encoded on the event horizon itself, accessible in principle to external observers. Through the holographic principle, the idea that all information within a volume of space can be encoded on its boundary. In the quiet space of theoretical physics, we contemplate the possibility that black holes are not information destroyers, but information processors transforming the quantum information they receive into new forms that are eventually returned to the universe through Hawking radiation. This perspective suggests that cosmic recycling operates not just at the level of matter and energy, but at the fundamental level of information itself. Let's drift into appreciation of the holographic principle and its implications for cosmic recycling. If the information content of a black hole is truly encoded on its event horizon, then the area of the horizon, rather than the volume, determines the recycler's information processing capacity. This connects black hole physics to the fundamental limits of information storage and processing in any physical system. Now we float toward understanding of how cosmic recyclers extract energy from their surrounding environment through mechanisms that go beyond simple accretion. The Penrose process, named after mathematical physicist Roger Penrose, provides a way to extract energy from rotating black holes through interactions within the ergosphere, the region outside the event horizon where space-time itself is dragged around by the black hole's rotation. Gently, we discover that the Penrose process operates through the splitting of particles within the ergosphere. A particle entering this region can decay into two components, with one component falling into the black hole while the other escapes with more energy than the original particle possessed. This extra energy comes from the rotational energy of the black hole itself, gradually slowing down the cosmic recycler while providing energy to the surrounding environment. As our journey continues through energy extraction mechanisms, we encounter the Blandford's-Naik process, which enables rotating black holes to power jets through magnetic field interactions. This process operates when magnetic field lines threading the ergosphere are twisted by the black hole's rotation, creating electric fields that can accelerate charged particles to relativistic velocities and launch them as collimated jets. Like whispers in the night, these energy extraction mechanisms reveal that cosmic recyclers are not passive processing centers, but active participants in galactic energy cycles. They can extract energy from their own rotation, from magnetic fields in their environment, and from the orbital energy of infalling material, converting these energy sources into radiation and kinetic energy that influences galactic evolution across vast scales. In the quiet space of galactic dynamics, we witness how cosmic recycling through black holes connects to star formation, galactic chemical evolution, and the large-scale structure of the universe. The energy released through accretion processes can heat and disperse gas clouds, regulating the rate of star formation and preventing galaxies from consuming all their available gas too rapidly. Let us drift into contemplation of feedback mechanisms through which cosmic recyclers regulate their own growth and influence their galactic environments. When accretion rates become too high, the resulting radiation pressure can blow away surrounding material, reducing the fuel supply for further accretion. and creating a natural self-regulation mechanism that maintains long-term stability. Now we float toward understanding of how jets launched by cosmic recyclers can transport energy and processed material across entire galaxies and beyond. These relativistic outflows can extend for millions of light years, creating cavities in the intergalactic medium and distributing heavy elements forged in stellar cores across vast volumes of space. Gently, we discover that cosmic recycling operates on scales ranging from the quantum mechanical processes, near-event horizons, to the large-scale structure of galaxy clusters. Each scale of recycling connects to others through physical processes that maintain the universe's overall energy and information balance, while enabling the complex structures we observe today. As our journey continues through the cosmic recycling story, we appreciate that black holes serve not as cosmic vacuum cleaners, but as sophisticated processing facilities that contribute to the universe's ongoing evolution. They recycle stellar material, redistribute energy across galactic scales, and may ultimately recycle the very quantum information from which all physical systems are constructed. Like whispers in the night, the mathematics of cosmic recycling reveals deep connections between black hole physics and the fundamental structure of space-time, quantum mechanics, and thermodynamics. These connections suggest that black holes may be windows into the deepest principles governing physical reality, offering insights into the nature of space, time, matter, and information themselves. In the quiet space of this cosmic perspective, we prepare to explore how supermassive cosmic recyclers at galactic centers orchestrate the evolution of entire galaxies, serving as cosmic conductors directing the slow, beautiful symphony of galactic evolution across billions of years of cosmic time. Beneath the quiet fabric of the universe, where light drifts slowly through the vastness and time itself seems to stretch into eternity, there exists a hidden rhythm guiding the birth, life, and death of galaxies. At the heart of this cosmic ballet, deep within the glowing spirals and luminous clouds of stars, lie the most patient and powerful recyclers the cosmos has ever created: supermassive black holes. These immense, invisible giants slumber in the centers of galaxies, shaping their evolution across billions of years, weaving gravity and energy into a story far older and grander than any single star. As we drift gently through the stillness of intergalactic space, we begin to notice a profound connection. These central giants are not solitary beings, nor are they passive spectators to the cosmic drama around them. Instead, they are intimately entwined with the galaxies that cradle them, growing and evolving together in a delicate, timeless partnership. This relationship is one of the most exquisite examples of cosmic balance, a silent, mutual shaping that ensures the stability and harmony of stellar communities across the ages. It is a relationship written into the very structure of galaxies themselves. The mass of a galaxy's central supermassive black hole correlates almost perfectly with the properties of the dense, stellar bulge that surrounds it. This deep connection, known as the M-sigma relation, whispers of an underlying harmony, a cosmic law suggesting that black holes and galaxies do not grow separately, but instead rise together, each responding to the other's needs. Across the vast range of galactic sizes and shapes, this proportional relationship remains astonishingly consistent. The black hole's mass is typically about 0.1% of the bulge. Mass, a precise balance maintained across billions of years. To understand how such a harmonious relationship emerges, we must follow the galaxies back to their earliest days, when the universe was young and still learning how to build structure from chaos. In those formative epochs, galaxies grew by pulling in streams of gas and dust from their surroundings, and by merging with smaller systems. At the same time, their central black holes, born from the collapse of the first massive stars, began their own slow and steady growth, feeding on gas and stellar material. This parallel evolution ensured that neither the black hole nor the galaxy ever grew too quickly or too slowly. Instead, they expanded in graceful synchrony, maintaining a delicate equilibrium that would shape their shared future. But the story of supermassive black holes is not one of quiet growth alone. At times, their peaceful slumber is stirred awake, and they enter a phase of intense activity, the era of active galactic nuclei. In these moments, the black holes become cosmic engines of astonishing power, devouring vast amounts of gas and dust through their swirling accretion disks. As material spirals inward, immense gravitational energy is converted into light, heat, and motion. The once invisible black hole becomes a beacon, radiating with such brilliance that it can outshine the combined light of every star in its galaxy. Among the most luminous of these active phases are quasars, the universe's radiant lighthouses. Fueled by torrents of infalling matter, quasars shine with a power that can eclipse entire galaxies, their light traveling across billions of light-years to reach us. Yet even in their overwhelming brightness, they remain governed by the same patient laws of physics that rule all black holes. They shine steadily for millions of years, their light a gentle reminder of the profound processes unfolding silently in the cosmic dark. This activity is far more than a spectacular display. It plays a vital role in shaping the destiny of galaxies themselves. As black holes consume matter and convert it into energy, they release powerful streams of radiation that ripple outward, influencing the very fabric of their galaxies. These energetic outflows heat vast clouds of gas, preventing them from collapsing too quickly into new stars. By doing so, they act as cosmic regulators, ensuring that galaxies do not exhaust their fuel all at once, but instead preserve reserves for future generations of star formation. This feedback, a delicate conversation between black hole and galaxy, helps maintain the slow, measured pace of galactic evolution. The influence of supermassive black holes extends even farther. From their blazing cores, narrow jets of particles are often launched at nearly the speed of light, piercing through the surrounding galaxy and stretching far into intergalactic space. These magnificent jets carry energy and matter across millions of light-years, sculpting the environments of galaxy clusters and enriching the cosmic web with processed material. Through this grand recycling process, black holes connect the life of a single galaxy to the evolution of the universe itself, bridging scales from the deeply local to the unimaginably vast. Our own Milky Way harbors such a cosmic recycler at its center, Sagittarius A*, though it lies dormant now, emitting only a soft murmur of radio waves. It contains the mass of more than 4 million suns. It has shaped the growth of our galaxy for billions of years, orchestrating the slow dance of gas, stars, and dark matter from its place in the galactic heart. Like a sleeping giant in a tranquil field, it waits patiently for the next chapter of its story, ready to awaken when the flow of cosmic material calls. The formation of these giants traces back to the universe's earliest days. The first stars, massive and short-lived, ended their lives as black holes, planting the seeds of cosmic recycling in the dense, gas-rich environments of young galaxies. Over cosmic time, these seeds grew, feeding on surrounding material and merging with other black holes during galactic collisions. With each merger and meal, they swelled to millions or billions of solar masses, becoming the gravitational anchors around which galaxies assembled. This coevolution between black holes and galaxies is a cosmic duet, played out over billions of years. As gas falls inward, it forms elegant, spiraling accretion disks, glowing with a warm radiance as they feed the central black hole. In turn, the black hole's feedback regulates the galaxy's star formation, preventing runaway growth and ensuring that the stellar population develops gradually and sustainably. The balance between feeding and feedback is so finely tuned that it shapes the very architecture of galaxies, from their central bulges to their spiral arms, from their star-forming regions to their quiet halos. The scaling laws that govern this balance, like the M-sigma relation, speak to an underlying unity in the cosmos. They hint at a universe woven together by deep, hidden connections where gravity, radiation, and time work in concert to create structure and order from primordial chaos. This interdependence is one of the most profound truths of modern astronomy. Galaxies and their central black holes are not separate entities but parts of a single, evolving system, each shaping and nurturing the other. Even the most dramatic manifestations of black hole activity, the powerful jets and glowing quasars, serve this deeper purpose. Rather than acts of cosmic violence, they are expressions of the universe's patience and balance. Jets, though launched with tremendous force, carry away excess energy and redistribute it into the surrounding environment. They heat intergalactic gas, prevent premature star formation in galaxy clusters and spread heavy elements forged in stellar furnaces across vast distances. In doing so, they fertilize the cosmic landscape, seeding it with the raw materials needed for future generations of stars and planets. This regulatory influence, known as active galactic nucleus feedback, is one of the universe's most subtle yet essential mechanisms. It acts like a cosmic thermostat, maintaining the conditions necessary for galaxies to thrive. Too much cooling and star formation would proceed uncontrollably, rapidly exhausting the galaxy's gas. Too much heating and star formation would cease entirely, leaving the galaxy barren and inert. Instead, the feedback operates in cycles, bursts of activity followed by periods of calm, pulses of energy balanced by stretches of stillness. Through this rhythm, galaxies evolve gracefully, neither burning too bright nor fading too soon. The fingerprints of this process can be seen in the diversity of galaxies that populate the universe. Elliptical galaxies, shaped by intense and early black hole activity, now drift in a state of quiet equilibrium, their star formation largely complete. Spiral galaxies, like our own, sustain a gentler, more ongoing process of recycling, with their central black holes quietly managing the ebb and flow of gas and star birth. Each galaxy, regardless of shape or size, carries within it the mark of its central recycler, a silent architect guiding its evolution from the shadows. As we float through this grand cosmic narrative, it becomes clear that supermassive black holes are far more than exotic curiosities or destructive voids. They are the beating hearts of galaxies, the engines of cosmic recycling, the guardians of balance and order in a universe prone to chaos. Their influence stretches from the smallest scales, shaping the lives of individual stars, to the largest structures in existence, linking the fate of galaxies to the evolution of the cosmos itself. And so, as the universe drifts onward through time, these ancient giants continue their patient work. They wait in the deep, quiet centers of galaxies, invisible yet essential, spinning the threads of gravity and energy that bind the cosmos together. Their story is one of partnership and transformation, of destruction that gives rise to creation, of silence that speaks of deep and enduring connections. They are the cosmic recyclers, the architects of galaxies, and the timeless companions of stars, and in their quiet embrace, the universe finds its most profound harmony. Let us drift into one of the most profound mysteries in our understanding of cosmic recycling, the black hole information paradox. In the quiet space of theoretical physics, this puzzle emerges like a gentle riddle whispered by the universe itself, asking us to consider what happens to information when it falls beyond an event horizon. In the gentle realm of quantum mechanics, we learn that information, the fundamental patterns that describe the quantum state of matter and energy, cannot be destroyed, like delicate butterfly patterns that must be preserved through any transformation. Quantum information appears to be a sacred aspect of reality that the universe protects with unwavering dedication. Yet as our journey continues into the peaceful contemplation of black holes, we encounter an apparent contradiction. When matter falls past the event horizon, classical physics suggests this information disappears forever into the black hole's interior, seemingly violating the quantum principle of information conservation. Gently, we discover that brilliant minds have proposed several elegant solutions to this cosmic puzzle, each offering its own peaceful perspective on how the universe might preserve information while maintaining the reality of black holes. In the quiet space of theoretical exploration, Stephen Hawking initially suggested that information might indeed be lost, a radical proposition that sent gentle ripples through the physics community. Later, in a beautiful example of scientific humility, he reconsidered, proposing that information might be preserved in ways we don't yet fully understand. Let's drift into the contemplation of black hole complementarity, a serene principle suggesting that information appears different to different observers. To someone falling into a black hole, information crosses the event horizon normally. To an outside observer, the same information becomes encoded on the black hole's surface, stretched and distorted but never truly lost. Now we float toward one of the most beautiful insights in modern physics, the holographic principle. Like a cosmic optical illusion painted across the fabric of space-time, this principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram encodes three-dimensional images on a two-dimensional surface. In the peaceful realm of black hole physics, this means that every bit of information that falls into a black hole might be preserved on its event horizon, encoded in subtle correlations and quantum fluctuations that we're only beginning to understand. The black hole becomes like a cosmic library, its surface containing the complete record of everything it has ever consumed. Gently, we discover that this holographic encoding doesn't violate our understanding of black holes, but rather enriches it, suggesting that these cosmic recyclers are even more remarkable than we initially imagined. They serve not just as gravitational recycling centers, but as cosmic information processing systems of unimaginable sophistication. As our journey continues through this theoretical landscape, we contemplate how quantum mechanics and general relativity might coexist peacefully in the extreme environment of black holes, rather than viewing their apparent contradictions as problems to be solved through conflict. We can see them as complementary perspectives on a deeper cosmic truth. In the quiet space of modern theoretical physics, approaches like string theory and loop quantum gravity offer gentle pathways toward understanding how these fundamental forces might merge into a unified description of nature. These theories suggest that at the smallest scales and highest energies, space-time itself might be quantized, woven from discrete quantum threads that preserve information even in the most extreme conditions. Let's drift into the peaceful realization that the information paradox, rather than being a crisis, represents an opportunity for deeper understanding. It invites us to expand our conception of reality, to consider that the universe might be far more subtle and interconnected than our current theories suggest. Gently, we discover how astronomers have learned to observe these invisible cosmic recyclers through their gentle effects on the visible universe around them. Like detectives following subtle clues in a cosmic mystery, we trace the presence of black holes through the beautiful dances they orchestrate among nearby stars and gas clouds. In the quiet space around black holes, stars follow elliptical orbits with mathematical precision, their motions revealing the invisible mass that guides their cosmic choreography. At the center of our own galaxy, astronomers have patiently tracked individual stars for decades, watching them swing around our central black hole in orbits that take mere decades, rather than the millions of years typical for galactic rotation. Let's drift into the peaceful observation of X-ray binaries, where black holes gently consume material from companion stars. As gas spirals inward through the accretion disk, friction heats it to millions of degrees, causing it to emit X-rays that telescopes can detect across vast cosmic distances. These aren't violent explosions, but rather the gentle glow of gravitational energy, being converted to light. As our journey continues into the realm of gravitational wave detection, we encounter one of the most beautiful developments in modern astronomy. In 2015, the LIGO detectors felt the gentle space-time ripples created when two black holes completed their final cosmic dance, merging into a single, larger recycling center. Now we float toward understanding how these cosmic recyclers create gravitational waves. As the black holes spiral toward each other, they disturb the fabric of space-time itself, sending out waves that travel at the speed of light across the universe. In the quiet space of gravitational wave astronomy, we've learned to listen to the universe's most profound recycling events. Each merger tells a story of stellar evolution, of massive stars that lived, died, and became black holes, only to find each other across the cosmic void and unite in a final, spectacular dance of cosmic recycling. Gently, we discover that these observations have opened an entirely new window on the universe, allowing us to study black holes directly rather than inferring their presence. Through electromagnetic radiation, the gravitational waves carry information about the masses, spins, and final dance of these cosmic recyclers, written in the language of curved space-time itself. Let us drift into the contemplation of one of humanity's greatest observational achievements, the first direct images of black hole event horizons. The Event Horizon Telescope represents a beautiful collaboration between observatories across our planet, working together like a single, Earth-sized eye gazing into the cosmic deep. In April 2019, This global collaboration revealed the shadow of M87 asterisk, the supermassive black hole at the heart of the galaxy M87. The image showed not the black hole itself, which by definition cannot be seen, but rather the glowing accretion disk around it, with a dark shadow marking the point of no return. This shadow appeared exactly as Einstein's equations predicted, a beautiful confirmation of our understanding written in light and darkness. Now we float toward the gentle revelation of our own galaxy's central black hole, Sagittarius A*. In 2022, the Event Horizon Telescope captured an image of this cosmic recycler that lies at the heart of our Milky Way home. Though much smaller and more variable than M87*, Sagittarius A* showed the same fundamental features, a glowing ring of heated matter surrounding a dark central shadow. As our journey continues through the observational landscape, we contemplate the beautiful X-ray astronomy that has revealed so much about cosmic recycling. In the peaceful realm of high-energy astrophysics, X-ray telescopes observe the gentle glow of matter being recycled through black hole accretion disks gently. We discover how binary systems containing black holes create some of the most informative X-ray sources in the sky. As material flows from a companion star toward the black hole, it forms an accretion disk that heats up through friction, eventually becoming hot enough to emit X-rays. These systems flicker and vary in brightness as the rate of material flow changes, creating a cosmic light show that astronomers can study to understand the recycling process. In the quiet space of X-ray observation, we've learned to recognize the signatures of different types of cosmic recyclers. Stellar mass black holes in binary systems create rapid, chaotic variations in X-ray brightness as they consume material in an irregular fashion. Supermassive black holes, by contrast, tend to vary more slowly and steadily, their enormous gravitational fields allowing for more stable accretion processes. Let us drift into the understanding of how X-ray spectroscopy reveals the composition and motion of material being recycled through black holes. Iron atoms in the accretion disk, heated to extreme temperatures, emit characteristic X-ray lines that are stretched and shifted by the extreme gravitational field, allowing astronomers to map the space-time geometry around these cosmic recyclers with remarkable precision. In the gentle unfolding of modern astronomy, the gravitational wave detectors LIGO and Virgo have opened our eyes to a universe filled with merging black holes, cosmic recycling events happening far more frequently than we ever imagined. Since that first detection in 2015, we've observed dozens of these cosmic dances, each one teaching us something new about how the universe recycles its most massive objects. Gently, we discover that these detections have revealed a rich population of black holes with masses we didn't expect to find. Some mergers involve black holes in the mass gap, a range where stellar evolution theory suggested black holes shouldn't exist. Others show evidence of black holes that merged from previous mergers, creating a cosmic family tree of recycling events stretching back through cosmic history. Let us drift into the peaceful realization that gravitational wave astronomy has confirmed one of Einstein's most profound predictions, while simultaneously revealing that our universe is far more dynamic than we imagined. Every few days, somewhere in the observable universe, the black holes complete their final orbital dance and merge into a single, larger cosmic recycler, sending ripples through space-time that eventually reach our planet as whispers of cosmic recycling. Now we float toward understanding how these discoveries have revealed the cosmic history of stellar evolution and black hole formation. The masses and spins of merging black holes tell stories of the massive stars that created them, of stellar winds and supernova explosions, of cosmic chemical evolution across billions of years of galactic recycling. As our journey continues through recent discoveries, we contemplate the profound beauty of humanity's first direct glimpses of black hole event horizons. The images captured by the Event Horizon Telescope represent not just technological achievements, but moments of cosmic poetry, instances where human curiosity and ingenuity allowed us to see the unseeable. In the quiet space of scientific discovery, the image of M87* revealed a supermassive black hole, actively engaged in cosmic recycling, its brilliant accretion disk glowing with the light of matter. being processed through gravitational forces beyond our everyday experience. The dark shadow at the center appeared exactly as theory predicted, surrounded by a bright ring of heated gas following the curved spacetime around the event horizon. Gently, we discover how the image of our own galactic center, Sagittarius A*, required even more sophisticated techniques due to its smaller size and more variable nature, like trying to photograph a firefly while it dances. Capturing this image required combining data taken within hours of each other, as the accretion disk around our local cosmic recycler changes on timescales of minutes. Let's drift into the contemplation of future explorations that will deepen our understanding of cosmic recycling. The James Webb Space Telescope, with its infrared eyes, peers back toward the cosmic dawn to observe the first supermassive black holes forming in the early universe. These ancient recycling centers, active when the cosmos was young, help us understand how galaxies and black holes grew together through cosmic time. Now we float toward upcoming gravitational wave missions like LISA, the Laser Interferometer Space Antenna, which will listen for the space-time ripples created by supermassive black hole mergers. Operating in the peaceful environment of space, LISA will detect lower-frequency gravitational waves, opening our ears to the cosmic recycling events involving the universe's largest black holes. In the quiet space of future ground-based astronomy, the next generation of extremely large telescopes will provide unprecedented views of black hole environments. The Extremely Large Telescope, with its 39-meter mirror, will resolve individual stars orbiting close to our galactic center, allowing us to test Einstein's predictions in the strongest gravitational fields accessible to observation. As our journey continues through the landscape of theoretical progress, we contemplate the gentle evolution of our understanding of cosmic recycling. New computational techniques allow scientists to simulate black hole mergers with ever-increasing precision, revealing subtle details of how space-time behaves under the most extreme conditions. Gently, we discover how advances in quantum gravity theories continue to illuminate the information paradox and other deep questions about black hole physics, string theory, loop quantum gravity, and other approaches to quantum space-time offer different perspectives on how the universe might preserve information while maintaining the reality of event horizons. In the peaceful realm of theoretical astrophysics, researchers are developing new models of black hole formation and evolution, incorporating effects from quantum mechanics, stellar dynamics, and cosmological expansion. These models help us understand not just individual cosmic recyclers, but the role that black holes play in the larger story of cosmic evolution. Let's drift into the understanding that theoretical advances often inspire new observational techniques, while observations challenge theorists to refine their models. This gentle back and forth between theory and observation drives the continuous deepening of our knowledge about these most mysterious cosmic recyclers. As our gentle journey through the realm of black holes draws toward its peaceful close, we find ourselves floating in a universe far more beautiful and interconnected than we might have imagined at the beginning of our cosmic meditation. These magnificent recycling centers, rather than being cosmic destroyers, reveal themselves as the universe's most sophisticated systems for processing, preserving, and redistributing matter, energy, and information across the vast scales of space and time. In the quiet space of cosmic contemplation, we see how black holes participate in cycles of creation and renewal that span billions of years. The matter that falls past their event horizons doesn't simply disappear, but becomes part of a larger cosmic story, contributing to the black hole-esque growth, influencing star formation in surrounding regions and perhaps carrying information forward in ways we're only beginning to understand. Gently, we discover that these cosmic recyclers exist at every scale of the universe, from stellar mass black holes that process the remains of individual stars to supermassive giants that help orchestrate the evolution of entire galaxies. Each plays its role in the grand symphony of cosmic recycling, ensuring that nothing in the universe is ever truly wasted, only transformed. Let's drift into the peaceful realization of our own connection to these cosmic recycling processes. The atoms that make up our bodies, the calcium in our bones, the iron in our blood, were forged in the hearts of stars and dispersed through space by stellar explosions, part of the same cosmic recycling system that feeds black holes and builds galaxies. Now we float toward understanding that we are not separate from these cosmic processes, but integral participants in the universe's ongoing recycling project. Our planet orbits a star that will eventually exhaust its fuel and die, returning its material to the cosmic recycling system. Our galaxy dances around a supermassive black hole that helps regulate star formation and chemical evolution across cosmic time. In the quiet space of this realization, we find not cause for anxiety, but reason for wonder. We are temporary arrangements of cosmic material, briefly organized into consciousness, able to contemplate and study the very recycling processes from which we emerged, and to which we will eventually return. There is something profoundly beautiful about being recycled cosmic material that has developed the ability to understand recycling. As our journey continues toward its restful conclusion, we contemplate the gentle lessons that black holes teach us about patience, transformation, and the deep interconnectedness of all things. These cosmic recyclers operate on timescales that dwarf human experience, some taking billions of years to grow, others existing virtually unchanged since the early universe. Gently, we discover that studying black holes has taught us about more than just these exotic objects themselves. They have become laboratories for testing our most fundamental theories about space, time, matter, and information. They have shown us that the universe is simultaneously stranger and more beautiful than our everyday experience suggests, filled with phenomena that challenge our understanding while inspiring new insights. In the peaceful realm of cosmic perspective, black holes remind us that even the most extreme and seemingly destructive forces in nature serve constructive purposes in the larger cosmic story. They teach us that transformation and recycling are fundamental aspects of reality, operating from the quantum scale to the cosmic scale with elegant consistency. Let us drift into the gentle understanding that our exploration of black holes represents humanity at its best, curious, collaborative, and committed to understanding our place in the cosmic order. The international cooperations that built gravitational wave detectors and the Event Horizon Telescope show us working together to explore the most profound mysteries of existence. As we conclude our meditative journey through the universe's ultimate recycling centers, we carry with us a deeper appreciation for the elegant processes that govern cosmic evolution. Black holes, those mysterious recyclers of matter, energy, and perhaps information itself, continue their patient work across the cosmos, participating in cycles of transformation that connect the smallest quantum scales to the largest cosmic structures. In the gentle darkness of space, these cosmic recyclers remind us that even in a universe that appears vast and indifferent, nothing is ever truly lost, only recycled, transformed, and woven into new patterns of existence. As you drift off to peaceful sleep, let your mind float among these cosmic recyclers, knowing that you too are part of this grand cosmic recycling project, temporarily organized stardust contemplating the recycling of stardust. The universe continues its patient work of recycling and renewal, and in that cosmic process, we find both our origins and our ultimate destination. Rest well in the knowledge that you are connected to these cosmic processes, part of a universe that wastes nothing and recycles everything with infinite patience and care. Good night from the sleepy scientist.